So solids, liquids. We have the change, the amount of heat that changes temperature, be equal to mass times specific heat times delta T. So that's for gases, it's different, and we'll go over gases later. But this is what we've learned so far. So, and also, so this is the amount of heat, which is in joules, which is energy, to change temperature. Okay? Specific heat, mass. All right. Also, heat of fusion is just changing change of phase, meaning liquid to solid, solid to liquid, liquid to gas, and vice versa. Okay? And that's again mass. And that's that depends on the material. So is this. Okay. All right. So far, this is what we learned. So let's use these and calculate some, do an example. Right. Let's do an example. Suppose I have a piece of ice. Okay. And I know its mass, so mass of the ice. And say the initial temperature is at minus 10 degrees C. This is very close to the ice in your freezer. In a freezer. Okay? Okay. How much heat, energy, needs to be added to the ice to raise its temperature to plus 15 degrees C? Okay, so this is a typical question. All right, I have some mass. I don't know, let's just say 100 grams, which is 0.1 kilogram. And it's at minus 10 degrees Celsius in the freezer. I want to heat it up until it's 15 degrees C. Okay, how much heat do I need to do this? What do I need to do, guys? Delta Q is MC delta T, and then? All right, that sounds like a reasonable thing. Why is this not correct? Why is this not correct?
Because the ice is gonna melt.
That's right, exactly correct. At what temperature does ice melt?
0 Celsius.
Right. So here's the thing. You have to be so careful. This question might be just, it may be a tricky one, but not if we have dealt with ice for all our lives, so we know what happens. Right? So the temperature, here's the temperature plot. We are at -10 to begin with, and I'm going to add heat until it gets to 0. While it's in 0, I'm adding heat, but not the temperature doesn't change. We already talked about that yesterday. But once it's completely melted, then it goes to a higher temperature. And I want to get it to 15 degrees. Okay. So then I have to calculate the amount of heat that I'm adding for 3 separate regions. Whoa. Okay, so I have to find it for this region, then for this region, then for this region, and add them all up. That would be the total amount of heat needed to bring a -10 C ice to +15, by which time it is just going to be water. All right, so let's calculate the amount of heat we need for phase 1. Now I can use this equation. Mass of the ice, C for ice, and then it goes from what temperature? T final minus T initial. T final is 0 minus T initial, -10. Okay? And the amount of heat I need for the second is mass of the ice times the heat of fusion of ice. And the third part is, again, now water, which is mass of the water, which is the same as mass of the ice, because it's the same mass. And this time we have to use the specific heat for water. Now, T final is 15, and T initial is 0. Okay? So these are the 3 that we need. And of course, let me see if I can find the values for M of the ice so we can actually carry on with this calculation. What is it? C ice is, well, I'll let you calculate this thing, but I'm just going to write down what this thing. C of ice is 2220 joules per kilogram times Kelvin. Now, of course, per Kelvin is the same as per centigrade because the divisions are the same. Delta T in C and K are the same. Now, and L of ice, which is heat of fusion of ice, is 333 kilojoules. That's 1,000 joules per kilogram. And C of H2O, specific heat of water, which is different from ice, is 4186. Again, with joules per kilogram Kelvin. So all you have to do is just plug in these with the 100 grams that I'm putting on top, which is 0.1. And then finally, the total heat is these 3 added together. So there's nothing mathematically difficult at all. In fact, the math is quite simple. Equations are really simple. It's really the understanding of what you need to do, which equation and how you need to deal with them. Other than that, everything mathematically is super simple. Okay? They are, of course. If I have 1 kilogram of ice, if it melts, how could that mass of water be any different? How could we didn't lose any molecules of water unless somebody drank some of the water when they were doing the experiment? I mean, if you have 1 kilogram of ice, you melt it, you still have 1 kilogram of water. Nothing disappeared on us. The mass did not disappear on us. We did not throw away the water, or we did not chip the ice away and throw it out. It's just conservation of mass. If you didn't take it away, it stays the same. Yes, these are the same. Mass of the water is equal to mass of the ice. Okay? So this simple example, you have to be a little bit careful. Make sure, because you know what happens to ice at 0 degrees, it's going to melt. So you can't just use these equations without getting into the details of what really physically happening. And physically, what's happening is the thing, it starts melting at around C, and then after it melts, then the heat you add will raise its temperature. But before that, it's just changing its state from a solid to a liquid. Okay? Is this clear? All right. All right, so let me go next to an example of gas, because gases are special only because they do a lot of other things that solids can't really easily do. All right, so let's create a container for our gas. All right, so I'm just going to create some sort of a cylindrical shape object and put insulator in here. So I'm going to have an insulator, a thick insulator like styrofoam or something. Okay, so some insulation. And this is a cylinder. And then I'm going to put some piston here. Okay? And this piston has a mass M. All right? And then I have this gas here. Now down here I have a piece of conductors, some thermal conductor, such as a piece of metal. Okay? A piece of metal is a pretty good conductor of thermal conductor, good thermal conductor. All right, so now what the gas is, and suppose the piston has mass M and also is covered with some insulation. So the gas can only exchange energy with the conductor at the bottom. So thermal heat can only come in and out from the bottom conductor, and I can control it. So I can control, suppose I have a knob to control it. Knob to control amount of heat. Okay? So the only, I can cool the metal down and then it sucks the heat out of the gas, or I can heat up the conductor at the bottom and it then dumps heat into the gas. but the gas is locked up with this kind of exchange with the bottom. It cannot exchange heat with the top or the sides because they're all insulated. Okay, so the gas can only be controlled in temperature or amount of heat you dump into it from the bottom. Okay, so this is clear. Okay, now before I do anything in the rest of the next few chapters, this needs to be understood. So the pressure here inside the gas, this is the pressure of the gas inside. Outside is the atmospheric pressure. All right, let's do free body diagram on the piston. Okay, free body diagram on the piston. Here's the piston. And I'm going to do a free body diagram. Well, here's W. Now, what are the other forces on this piston? What are the other forces, guys?
Gravity.
Yeah, that's the W. I wrote W, which is the weight.
Sorry.
What else? Right. What are those? So there is the gas is pushing it up. So this is the force due to the gas. And the force atmosphere is pushing down, force of the atmosphere. Right. Okay. That's it. And then I can just say, oh, it doesn't matter what I call X. Here's X. All right. Now, if nothing is moving, if the piston is just there sitting doing nothing, then the sum of these forces by Newton's second law should be equal to 0 because there's no motion, no acceleration, no nothing. So F of the gas minus F of the atmosphere minus mg, they all have to add up to 0. Right? So you get F of the gas, then minus F atmosphere minus mg is 0. Then F of gas is F of atmosphere plus mg. All right? Now, what is the force of gas on that piston? What is the force of the gas on that piston? How is it related to the pressure of the gas? Huh? Do you guys remember the definition of pressure? What's the definition of pressure? Pressure is equal to what? What is the definition of pressure, guys? That's right. So what would be the force from that equation? Wouldn't it be pressure times area? So F of the gas is pressure of the gas times the area of the piston equals pressure of the atmosphere times the area of the piston plus mg. So from here, I can then write P of gas is P of atmosphere plus mg over A. Okay? So you see, if I have a piston with some mass there, I have the pressure. Now I have a relationship between the pressure of the gas inside the cylinder and pressure outside, which is the atmospheric pressure. That's the equation that relates these two. Let's look at this a little bit more careful. So P of the gas is P of the atmosphere plus mg over A. And of course, the atmospheric pressure is known. Do you guys remember what the atmospheric pressure is? Isn't it like 100,000 Pascal or something? Yeah, so that's roughly 1 times 10 to the 5 Pascal. Plus, let's give these some reasonable numbers. Mass of the piston, say it's 1 kilogram. That's pretty heavy, but hey. We already know the G acceleration. Let's say the area is 9.8 meter. Well, that's really large. Let's say it's, I don't know, some cylinder that the diameter is like 10 centimeter. So it's pi r squared, pi, say 0.05, 5 centimeter radius squared. All right. So what is that number? Let's calculate it. So 0.05, that's 5 centimeter. Squared times pi times 9.8. So this is roughly 1247 Pascal. But if you look at it, let's keep it that way. But 1 kilogram is too heavy, but who cares? Okay, so now I have what? I have 1,0,0,0,0,0 Pascal plus 1, let's say 1,2,0,0 Pascal. All right, so the final answer is what? 101,200. So you can see how close this is to atmospheric pressure, because the second number here is much, much smaller than 1 atmosphere. So you can always assume if it's normal weights and stuff, not if you have a 5-ton piston. But if this is an example in the lab, you can see that the P of the gas is roughly equal to P of the atmosphere, which is a constant. Well, it was a constant even on top. Okay, so this is also a constant. Okay, so you can see P of the gas is a constant. And it's roughly equal to the atmospheric pressure. Okay, so it is a constant, and it's roughly the atmospheric pressure with the normal weights of the pistons and areas and all that. But nevertheless, it is constant because the mass of the piston is the same. G is a constant, A is a constant, P atmospheric is constant. So it's a constant pressure. So no matter what happens in this experiment, no matter what happens here, the pressure of the gas inside that contraption is roughly equal to the atmospheric pressure. Okay? All right. So why am I saying all this stuff? Well, here's the reason. But
Professor?
yeah.
Is the piston a cylinder?
Yeah. What do you mean by that?
Because I'm a little confused with why you put pi r squared for the area.
Yeah, well,
Is it
let's
just
say
like
this is r, radius of the piston, and the area of the piston becomes pi r squared. I mean, okay, so let me draw this way. Here's the piston, and
Okay.
here's the cylindrical jacket.
Okay.
You
Okay.
see it?
Yeah, thank you.
Okay, so that's how it looks. Yeah. Okay. All right. So, because a lot of the problems in the book and examples are shown using this methodology, and they never explain exactly what they mean when they say, "Oh, the pressure of the gas is atmospheric pressure in this system." Well, how? I mean, you have that piston on top of it. Obviously, the pressure is larger, but not by much. You can see it's pretty close. Even when you put a 1 kilogram piston, which is pretty heavy, it's 2 pounds, that pressure in the gas is not much different from it. But no matter what, the pressure of the gas is constant. Is constant. If the piston is allowed to move up and down, it is a constant. Okay. All right. So imagine that kind of an experiment where the piston is there and all that. Okay. Now, suppose this piston, suppose this pressure of the gas goes up a little bit. Just a little bit. Okay? So pressure of the gas goes up a little bit. And what happens is what I mean by that is that if the volume of the gas goes up, so volume goes up. All right? So let's say initially you have this volume, and then later on the volume changes, so it changes the position of the piston, and this is your V plus a little bit of change in volume. This is the new volume. Okay, a little bit of change. Okay? Now, that little bit of change, if you consider the area of the piston, is just simply this distance, let's say ds. So dV is really just the area times ds. As we can tell, the volume change is this much. This is the change in volume. And that's equal to the area times, for a cylindrical geometry, it's equal to the height of that thing times the area. So that's dV. Okay? If during all that time, the pressure of the gas stays constant, which it does, because it's roughly equal to the atmospheric pressure outside, so the amount of work done by the gas, by definition, of course, is F dotted to ds. But that force, the force is pushing up, and ds is going up, so this is just F ds, because they're both in the same direction. The cosine of the angle is 0. And ds, and the force is, of course, pressure times the area. Okay? But what is this thing? Well, that's this. And this amount of work is really infinitesimally small amount because the volume changed infinitesimally. So this is dW, the infinitesimal amount of work done when you move the piston by changing infinitesimal amount of volume, and it moves it by an infinitesimal amount ds. So dW then, done by gas, is equal to P dV. So the total work done by gas is therefore the integration of P dV from the initial volume to the final volume. All right, so that's the amount of work done by the gas. So we just derived for gases the amount of work done when the gas changes from initial volume to final volume. And we did this thing directly from F dotted to the displacement, the direct definition of the work, but now applied to gases. All right, so work done by gas is equal to PdV. What does that mean at all? Well, we're going to plot pressure versus volume for the gas. And suppose the pressure goes in some direction like that. That's the function for pressure. Now you want to find out how much work was done by the gas going from this initial volume to this final volume. Well, according to that integration, this area under this curve between those two limits is the amount of work. This is the work done by gas going from V initial to V final. Okay? It's just the definition of that. The integral is always the area under the curve. That's what it is. All right. And when we say initial to final, we mean we're moving in that direction. Okay. All right. So that's the definition. That's the formula for the work done by a gas, which is the integration of pressure times dV when it goes from one volume to another. And graphically, this is what it means. Now, there's all sorts of scenarios. All right. Here's one. If we go this way, from some initial to some final, the area here, the work done is greater than 0. All right, so this work is greater than 0. This is the work done by the gas. All right. Now you can have another situation where you're moving in that direction. This work is negative. Okay? The gas is doing negative work, but by expanding, its volume is getting larger, so it's expanding. All right? There's all sorts of other possibilities here. You can go in this direction. All right? And the total work, of course, is this. This is sorry, this is greater than 0 again. All right? Or you can have another possibility here. You can go like that and then come back. All right? Now this area, this amount of work is still positive because that's the amount of work the gas has done. So you can see, graphically, you can tell a lot. You can tell a lot by just looking at the plot, and they're going to do a lot of that for you. So be careful. You could have a thing like this. What is that amount of work? Positive or negative? This is negative. It looks like the other one, but I'm going the opposite direction. Remember? The area under this curve is positive, is negative because of this. But then on the other end, it looks like this. So when you subtract the two, the red area has a net negative number. Okay? So there is a lot of things that you can tell by looking at the plot of P versus V. All right? Okay. Any questions? All right. Internal energy. Okay, the internal energy change in internal energy is equal to the amount of Q added to the system minus the amount of work done by the system. Okay? But that should be obvious, right? The internal energy is the amount of heat that you add to the system minus the amount of work the system does to the outside. So one of them is adding energy, the other one is subtracting energy, obviously. So this is the internal energy, and it is a state function, meaning it only depends. This is a state function. It only depends on the initial and final states. Okay? So it only depends on initial final state. It doesn't matter how you get there. The amount of work does, the Q is and all that, but the internal energy doesn't. Okay? So the internal energy is only a function of the endpoints. Doesn't matter how you get there. Does not matter how you get from initial to final state. And of course, I'm going to do some examples. You'll find out final state. Okay? It doesn't matter. Internal energy doesn't matter. Work does. The other ones do, but this one doesn't. Okay? So the internal energy of the system depends only on how much heat you add to the system and how much work that system does. And when you subtract the two, you get the total internal energy, regardless of how you get those places, how you change those. Okay? All right. So I'm going to rewrite it again. You have to be careful. Work is a tricky thing. You always have to know what they're asking. You've seen this. When I did the example of lifting a mass to a new height, the amount of work done by me was positive, but the amount of work by gravity was negative. So it all depends on work either being done by the force or you have to always find out which force they're talking about. Okay, so this is when the system itself is forcing. So work is a tricky thing. You need to definitely remember what it means. Which force are they talking about? In this case, it's the force done by the system, which in this case is gas. Okay. All right. There are a few processes, okay, that a system can go under, that a system can undergo. Okay. One, adiabatic. That's an adiabatic process. What does that mean? It means the amount of heat added or subtracted from system is zero, which means that the internal energy of the system only depends on the work done by the system, because Q is zero. All right, adiabatic means Q is zero. Okay, that's one of them. And we'll get to these things when the examples show up, and you'll get to there's an adiabatic process happening, this is that, and then oh my, that means Q is zero. Okay, so that's one thing. There's a constant volume. Okay, constant volume means because work depends on change in volume, constant volume means work is zero. Okay, which then means change in internal energy only depends on how much heat goes in and out of the system. Okay, that's the constant volume, meaning work is zero. Okay, 3, there is a thing called cyclical process, which means if the system goes from initial to final state, it comes back to the initial state. That's why it's called cyclical, because like a circle, it goes back to itself. Okay? And remember, the internal energy change only depends on the initial and final state. So if it goes back to initial state, that means delta E internal is zero. Remember, that was the whole point of being a state function, which then means Q is equal to the amount of work done by the system. Okay, so, and then there is a fourth one, free expansion. Now this thing really depends, it really is a gas thing. Okay, a free expansion means Q is zero and W is zero, which then means the internal energy stays constant. So change in it is zero. Okay, so, and what we'll do some, let me just summarize this thing so we know we have it in a chart form so we can deal with it. And we'll do some examples, of course, if you have time. But let me, or we can just do it next time we see each other tomorrow. So the process, there is the requirement, and there's a consequence. Okay, so there's adiabatic. And that means the Q is 0. That means the internal energy is just the amount of work done by system. And then we have the constant volume, which means we cannot do work, of course. And then the internal energy only depends on the amount of heat. You either add or subtract it. And then cyclical, which means by definition of the internal energy, that would be 0, which then means Q and W are the same. And these become tricky when problems show up later. And free expansion means both Q is 0 and W are 0, which then means internal energy is constant. So change in it is 0. So let me get us. All right. So these all are sort of really, really related to this piston setup that we talked about. And we will do some examples for you to see. It's not entirely with only gases, but only with gases you tend to notice volume changes. If I heat up gas, if I heat up a balloon, a birthday balloon, you can see it physically getting larger. So the gases show volume change enormously more than if you heat up a piece of spoon. If you get a spoon and heat it up, you don't see its volume changing and changing its shape into twice as much size, because solids and liquids do not change much in volume, but gases do. Even though these equations are all true for all sorts of stuff, it is in gases that we see them very clear. And that's why we do a lot of examples with gases. But it's not necessarily need to be gases. All right, I will see you guys tomorrow morning then. You guys take care. Any questions before I leave you?